All right. Hello everybody. This is our first workshop for theory track. This quarter, this is also a brand new workshop. So sorry for the hiccups and inconveniences at the beginning. We're still all figuring this out. But yeah, we're gonna get started now.
First, some of y'all may have heard workshops is different this quarter. Who here was at the kickoff? So I know if I need to go through this again. Okay, who here was not at the kickoff? Okay, so we have some people. So I'm just going to quickly clarify what's going on, right? So last quarter, we had advanced track and beginner track, right? That worked okay for a few years, but then what we have realized is that it gave people very little time to have hands-on things. And then the parts where you do want to talk about the theory, because we're forced to also do hands-on at the same time, it just diverted from that. So instead of doing that, this time we have kind of split workshops into two tracks that run concurrently, theory track and applied track. Where applied track is where you get like actual hands-on experience working with PyTorch, building your own ML models. Theory track is where you come join to learn about the things that we won't get to in applied track, because at the current stage, it is too complicated to implement, but we think it is very important for you to know about, like a more advanced topics such as, large language models, deep differential models, really delving into things like optimizations, stochastic gradient descent, and stuff like that. That's what's going to be happening in theory track, and that's what's going to be happening in this room every Monday until week 9. So yeah, just a quick, applied tracks is where people just want to know the practical bare bones. If you want to do projects in the future and you have not done advanced track, say last quarter, we would heavily recommend going to this. Who here is not in applied track? Okay, so we have like 3 people, but you guys probably already have like PyTorch knowledge to begin with. If you don't, I heavily recommend you go, because because this, we're not really going to have a lot of coding. It's mostly going to be, here is why machine learning is the way it is, right? These are very important problems that may not exactly seem like very crucial now, but like the more you get to doing the practicals, the more you realize this is going to be very helpful. So that's what applied track is for, and we heavily recommend it. Again, it's 4 self-paced notebooks. We hope everyone's going to end up here, but this is going to prepare you for projects. For theory track, which is what we're actually doing today, it is for people who are here, which is for people who really want to know machine learning. And again, we heavily recommend it for project track, even though it's not required. Because if you want to do any form of, say, machine learning research in the future, or be, a good machine learning scientist, or even have that sort of theoretical backing to be able to create cooler projects, this is just beyond the things that project track is offering you, this is going to be very helpful, because you will know at least the terms to look for in the future when you're, say, looking for ideas to make cool projects. This is a bit of a roadmap that we're currently looking at. So we're going to talk about gradient descent and neural networks today, but we also have week 4, we have some CNN stuff, we have RNNs. We're going to talk about this stuff, which is really cool. And also we're going to talk about large language models, we're going to talk about deep learning models like Stable Diffusion. So we have a lot this quarter. All of this are tentative. If you have anything that you want us to talk about, but it's not on the list, feel free to talk to us after the workshop, or just let us know on Discord. Okay.
All right. Sparsh.
Hello, I'm Sparsh. I'll be handling like more of the applied track. What are the applied track notebooks? And then I'll be also helping out with like questions and stuff over the course of theory track, and hopefully I can like facilitate you guys learning some of the more advanced concepts that we're going to be covering throughout the series.
I'm Vegas. I'm a 3rd-year CS major. I'm trying to write the theory track content, and so when we say it's tentative, that means I'm still writing that content. So if you guys want to see certain content or stuff like that, feel free to ask us, talk to us. Gord is also like really knowledgeable, so he will also be teaching possibly certain workshops of theory track. And then our 3rd officer is Liu. He's not here yet, but he's also really good at theory track stuff, and he'll be doing a couple of those presentations. And then we have one more person who's also not on here, our team. He'll probably be doing like the large language model stuff and transformers for theory track whenever that comes up. All right. With that out of the way, we're gonna. This is the schedule for today. So this is quite a bit. I will be going slightly fast. So at the beginning, it'll be slightly slower, not too much math. And then by the time we get through 3 and 4, the math will be very heavy. And it's okay if you guys don't follow that math. We'll just be throwing math symbols at you. Hopefully, like, you get some intuition about what these symbols mean. That's all we're hoping for. So next time you see these symbols in a research paper, it's not your first time looking at these. You'll be like, oh, I've seen these. All is good. Then we're going to go into stochastic gradient descent and constrained optimization. these are like more fun topics, just a little bit more like ML heavy, not as math based. So that is the plan. And then finally, neural networks. We'll have a brief introduction to neural networks, but next week's workshop will be more focused on the math of neural networks, backpropagation, and convolutional neural networks. Okay. Also, we have to give acknowledgments to these two professors, Professor Raghu Vega. If you ever have a chance to take a class with him, highly recommend it. It's probably one of the best professors here at UCLA, and also Professor Grover. About 100% of this content was stolen from them. So, yeah. Okay, so we're going to start off very basic. We're going to formalize what does it mean for a machine to learn something. And so hopefully by talking about this, we can also end up with a mathematical formulation for how we want to view machine learning and how we can actually then kind of mathematically inspect it and prove things about it. So there are kind of, can anybody name like different learning problems that maybe exist that you see, right? So a learning problem in this case can be a planning problem, right? You maybe have a schedule and you want to create some machine learning model that will optimize your schedule for you. Probably something that's more common and that you guys have heard of is classification problems, right? Clustering, things like that. And then stuff that's more recent and very hot in the field right now, generative models. So how do you generate images? How do you generate new things? So these are all types of learning problems, right? We're trying to create and we're trying to build something new. Theory track will be primarily, at least this one, will be focused on something called supervised learning. And basically what supervised learning is, it means that we have labeled data. So basically whenever you have, let's say you have a set of images, right? Each of those images will have a corresponding label. So if you have an image of a dog, you'll have a labeled dog associated with it. If you have an image of a cat, you have a labeled cat associated with it. And that's going to be really important when we start talking about gradient descent and stuff like that, because some of that doesn't work with unlabeled data. Unsupervised learning is the other portion of machine learning where you don't have labeled data. And that is where you will have clustering and stuff like that, where you don't necessarily have a label, but you're trying to discern these differences in your data. Any questions so far on like this high level stuff? All good? Cool. Okay. So as I said, we're going to focus on supervised learning for today. And so we're just going to formalize that. So supervised learning, we have a data set. And this data set will have a feature x1, and each feature will correspond to a label y1. And so in the case when we were talking about images, x1 is like the pixels that compose the image of a dog, and y1 would be the actual label of a dog. And so basically our data set will consist of many of these images, or as we're saying right now, features, and we'll say we have like n such features, or n such entries in our data set. And it's important to note here that n can be very, very large, to in the millions in modern machine learning algorithms. And we will kind of see why that becomes an issue this workshop.
For example, Lion 5B, which was used to train Stable Diffusion, has 5B, aka 5 billion image text pairs in its data.
Yeah, so a lot. So n is not like just a small number here where it's like 100 or 200, where it's in the millions and to the billions. So we have this data set, and basically what we're trying to do is we want to, given a new x value, we want to predict its label. So we have a bunch of like previous information, and now given some new information, we want to deduce what its label is going to be. Okay, and so basically what we can think of this as is this data set, we'll call it our training data set. So this is what we're going to use to try and learn these patterns, learn these different things to minimize something. And then we are going to test it on our testing data set. Okay. One thing that we often kind of don't mention about machine learning and why machine learning actually works is that we assume the train and test data set come from the same distribution D. So we say that all of our samples come from some distribution. Some of them are part of our test, some of them are part of our train. And basically what that means is when we try and generalize to our testing data set, we have a higher chance of doing well on our train. Oh, misspoke there. When we generalize well to our training data set, we have a better chance to generalize well to our testing data set, right? And that is all because we say they are coming from like the same location, right? For example, if I created a model that was purely maybe, let's say, for like the English language, I cannot guarantee that this will generalize well to, let's say, any other language right now, right? But if you were sampling your data properly and you had a mix, then maybe if you had a mix of English, Spanish, Mandarin, Hindi, et cetera, you can generalize better. So this is really important. We don't talk about this portion right here. That is something called statistical machine learning, and that will give you the relationship between those two. But we just focus on optimization. Okay. So what are we actually trying to do? So far we've said that we have some data set.
Yeah, I mean, it's more like.
And what is our goal here? So we want to somehow create some model, which we will now call just a function, any function that you can see in any of your math classes. And we want to produce a function that models this data the most accurately. So for example, how many of you have heard of linear regression here? Okay, so quite a few. That's good. So linear regression is something in the form of y equals ax plus b, right? So if you have a linear data set, you're trying to find the line of best fit that will model that data. And so basically your hypothesis class is basically this. Ax plus b. And theta, or your parameters that you're trying to optimize for, are a and b, right? So basically the form is the same. So h theta denotes the form of your function, right? So when you say like a linear equation, you always go to ax plus c. When you say quadratic, it's x squared. Ax squared plus bx plus c. Cubic, so on and so forth, right? The form is the same, but there are these like constant factors in between all of these that we can change to create these really different looking functions. So what we're trying to do is we're trying to learn those parameters. And that is what all of this fancy jargon right here is saying. The parameterized hypothesis class is linear, quadratic, et cetera, et cetera. And then the parameters theta are what we're trying to optimize for. Okay. Do we have any questions so far? So does this notation make sense right here where I've written h theta of x? What theta is, what h is? Okay, cool. But so we've spoken about, okay, our input, our output, what we're trying to learn, but how are we actually going to measure our performance here? That is something called a loss function. And so all the loss function does is it takes two inputs, two labels, and it'll output a score depending on those two labels. So for example, back to like image classification, if you classified a German Shepherd as a golden retriever versus the same golden retriever as, let's say, a cat, you should be giving different scores to those, right? Because one is a completely different animal. So what our loss function does is it takes in two inputs, A and B, and it outputs a score. And generally speaking, the lower the score, the better we're doing. The higher the score, the worse we're doing. So when we're thinking about this, we have some, function that we're trying to learn. We have a set of like true values that we know, which is our data set. And now we have a way to measure the difference between our predicted and our actual expected values. And so now the question that I'm going to ask is, what do we actually want to do with all this information, right? So I have something of the form here. Right? And so what is this summation saying right here? This summation is saying that we will make a prediction. So this is our prediction. And this is our expected value. And we compute the loss between those two values. And now we're summing that against all of our samples. So we do this for each sample, right? If you have 1,000 samples, you take your first sample, you make a prediction, you compare it to your expected value. Now you have a loss value for that. You do the same thing for your second sample, your third sample, your fourth sample, so on and so on. So this is basically our entire loss function, right? And if you recall, the lower the loss, the better. The higher the loss, the worse. So what are we actually trying to do? We're trying to minimize this. Everybody clear on kind of the formulation here? And so there's really only one parameter we can vary in this entire scenario, and that is just our theta values, right? H is like a fixed function, right? We were saying H is quadratic. You can choose a different function, but we're not really optimizing for that. We're trying to optimize for those A's, B's, and C's. So basically, we put that all together, we get this fancy notation. 1 to n So this is what we're trying to solve. Whenever we see supervised learning, every supervised learning problem can be modeled by this function right here. You have some loss function, you have some prediction function, and you're basically trying to minimize your errors. Now, there's one symbol that you've not seen here, and this is this little H in a circle. And that will come into play a little later in this workshop, but that is the set of all allowable parameters. So for example, in a linear equation, y equals ax plus b, a and b can be any real value, right? So your set of all allowable parameters is part of all of the real numbers. Now, the reason we include that is there are certain scenarios where you may not want certain values. For example, can anybody tell me like a scenario where we don't want negative values as like a weight, right? Any ideas? All right, let's think about maybe like house price or just money, right? If you want your model to have some sort of semantic meaning, right? Generally, people do not negatively weigh money into certain things. So we would say that we only want numbers that are greater than or equal to 0. And this makes our optimization problem a little bit harder, right? We're not able to just say data can be anything we want. We have to say, okay, we need to find a data such that it is still greater than or equal to 0. And so basically, this is just that fancy notation for saying, hey, in the future, you may see a problem where, you know, you can't use any real number. And we'll talk about that in a bit. Okay. But so far, any questions on this formulation for like machine learning and stuff? Okay, cool. Then we're going to get into gradient descent. So gradient descent is this amazing algorithm that we're going to talk about for basically the majority of the workshop now. So that function that we wrote initially can be modeled by like a loss landscape. In 3 dimensions, one loss landscape will look like this, another will look like this. And remember that we're trying to minimize this. So we're trying to find the smallest point on somewhere on here. So now imagine that this is a mountain range and you are on a hike and you want to find the lowest point. What would you all do? Let's say you just start maybe right here and that one compares you. Let's say you start right here and like the minimum point is somewhere over here. How do you know that that is the minimum point? Any ideas? Like you're just hiking. Yeah. You keep going downhill. And so that is all gradient descent does. You have a starting point and you just go downhill. So what we want to formalize is what does it mean to go downhill? And that is in the name itself, it is the gradient. So the gradient of a function at any point is the maximum increase. And so if we want to go downhill, we take the negative gradient, which will give us the maximum decrease. So for those of you who have done CS 180, gradient descent is a greedy algorithm. We are basically just choosing at our current situation, what is the best direction to move forward in, and we do that. All right. So if we have an initial position, xi, what we want to do is we want to take a step in some direction. And what is that direction? That direction happens with respect to the gradient.
Go back here, Dana.
So this is basically the gradient descent algorithm. You just keep repeating this update step. You're at a point. You calculate the direction of steepest descent, and you take a step forward. That is all that's saying. And we just keep repeating this until hopefully we reach a local minimum. Okay? Any questions so far about this equation? Any questions about like the step size and stuff? Okay. So I do want to make a point about this value right here called the step size. So this value is very important. If I gave you a function that's just quadratic as follows, and let's say right here, if I gave you a very large step size, your gradient points you in this direction. So you're going to be moving in that direction. But if your step size is very large, you may hop over to this other end. Is that really good for us? Probably not. You're making progress here, don't get me wrong, but if your step size is large enough and I give you a very weird loss function where at this point it was significantly higher, you would not like that. So we need to choose a step size where we're not going to be hopping between two values, back and forth till convergence. So some of you may suggest that, oh, let's take a very small step size. you know, let's play it safe. We'll just go teeny tiny bit all the way down. And this is good. But as we'll see later, if you have millions of samples, this will take forever. And this will never converge. You will never find your optimal solution. And we don't like that because then we're not solving our machine learning problems. So basically the entire point of today's workshop is how do we prove that there exists a step size for certain functions that will guarantee us to reach a local minimum, a global minimum rather, within a certain amount of time. Okay. So that is kind of one of the issues that we discussed with kind of the step size, but just based on hearing this algorithm right now, right? Can anybody else think of like any other issues that may arise when we do gradient descent? Yeah. Mhm. Yes. So if we have multiple local minimums, how do we know which one is going to be our global minimum? How can we guarantee that we get there? We will see that there's actually no guarantee for that. But yes. Yeah.
Also, like the issue of like how do you choose a starting point?
How do you choose a starting point? That is a very good one. So if I gave you a function as follows, and if I started right here on the left, you will converge to this point. We can all clearly see that this function that's not the best solution, right? It's not the lowest point. But let's say I started somewhere over here. I will converge to this point. And now we're actually at the best solution. So how do we choose the starting point? Any other ideas on like issues, problems? Gradient descent has a lot of problems. So we'll get into all of those, but all right, good start. So here are kind of the big ones that we'll be talking about. The first one is, will it find a true minimum, right? So that was your question. We don't know if we have two local minimums, will it really converge to the true minimum? Answer to that is, it will not always. How many steps does it take to run? So that was an entire spiel about, oh, choose a large step size, you're going to be going back and forth. Choose too small of a step size, you'll never converge because you're going to be too slow. How do we compute the gradient? So far, we've just said, oh, we can just take the gradient of a function. Life's good. That's not really always the case. So 2 and 4 are kind of related to each other. How do we choose a good step size? How do we choose the starting point, as you said? And then when does the algorithm stop? If you realize I just said, oh, we just run it and we hope something happens and we converge. So how do we stop this algorithm? When do we know that we've reached an optimal solution or a solution that's good enough to us? And then if the gradient is really difficult to compute for certain functions, are there any surrogates? We'll just answer that question really quickly. There is something called the subgradient. You are welcome to search it up. It's basically looking at the tangent lines near points, and it does some fancy Taylor series stuff. But we won't really be getting into that. But the answer to that is yes, there's a surrogate function that will make the gradient a little bit easier to compute. Okay, so that is the gradient descent algorithm. Now we're going to get into a little bit of math to discuss how we can prove that gradient descent will converge for certain functions. Okay, so the first thing we're going to talk about is something called a smooth function. So if you recall, I can draw two functions right here. One that looks like this, and one that looks like this. Clearly, one will be nicer to optimize than the other. So the one where it's really jagged is going to be very sensitive to our step size, right? We have to really fine tune our step size, and we really need to think about, oh, you may want to pick a smaller step size because if you take too big of a step size, you can start over here, and God knows where you'll end up. You can end up over here, and that's just not good. But if you have a nice function like this that's smooth, you can maybe afford to take a little bit of a larger step size, right? You're not going to be going all over the place on your function. And the mathematical way of saying that is we talk about beta smoothness of a function. So this is just going to be definitions right now. But what we have is this. So we say for all x comma y are just points. You can think of everything we're doing right now in just 2 dimensions, and it will work fine in n-dimensional cases. Okay. So basically what we're going to say is we're going to take the gradient between these 2 points, so the difference in the gradient, and we want that to be proportional to the difference, the Euclidean difference between the 2 points. Let me rewrite that. That was horrible. So basically what this is saying is the change in our gradient between 2 points is with respect to the actual distance between our 2 points. Okay. So this will not make too much sense right now, but a really nice example is x squared. So let's take x squared. What is the gradient of, or let's say we take, what's another variable besides x? Z squared. So now what is the derivative of z squared? 2z? Yes. So that is 2z. Now remember x and y are just 2 arbitrary points. So let's go ahead and plug stuff into this equation. What we're going to get is the gradient of f of x. So if we say f of z equals z squared, delta f of z is equal to 2z. So that means delta f of x must be 2x. And this is just going to be 2y. And this should be less than or equal to beta multiplied by x minus y. And now if you see, we can factor out a 2 here. We get 2x minus y. That's going to go to beta minus y. And what value of beta makes these two inequalities true to each other? Any ideas? 2. So beta, as long as beta is greater than or equal to 2, this inequality holds. And so basically what we're saying is x squared is a too smooth function. Okay. So if you all did like advanced or beginner track, you'll recall we have a loss function like called MSC, which is kind of in the form of a minus b squared. And the reason we love working with squares so much is because it is a too smooth function. It is a smooth function, which gives us a bunch of optimization galore. And we just love it because we can do a bunch of guarantees for it. We'll also see that this loss function is also convex, which will answer the question of having multiple local minimums. But that is the definition of smoothness. All you need to really know is smoothness is talking about quite literally how smooth a function is. We don't want our gradient to be changing too much. We want it to be changing with respect to the difference in our actual points. So smoothness allows us to define something called a smoothness upper bound as well. And basically the smoothness upper bound is something based on a Taylor series expansion. And all that says is we will never be increasing past a certain value within any difference. And this is the smoothness upper bound. F prime of So basically what this is saying is our function value here will never be, it'll always be less than this value. We can never go past this value. Okay. So that's coming back to the entire idea. We're not changing too much. We don't like change that much, right? Because if we have too much change, we don't know what's going to go on in our function. And basically what happens is if you combine this function and our gradient descent algorithm, so the gradient descent update step, what we can actually prove right away right now is that gradient descent will always make progress given a smooth function. So what does that mean? If we go back up here, if we were to step somewhere, there's a chance we can end up somewhere higher than when we initially started. We do not want that. That is not good. We're not making progress. So what does making progress mean? We can always guarantee that we will be moving forward in such a way that our values will always be less than the previous value. So we're going towards a smaller value, which means we're heading towards a minimum of the function. So we can do this one proof. We will probably skip the longer proof for today because I think we're going to run short on time otherwise. But this proof is fairly easy. So recall the gradient update step, this. So here's the smoothness upper bound. If you see f of x of I plus 1 is in this form of a plus 8, where a is going to be xi, and h will be the step size multiplied by the gradient. So basically what we are saying is on the next iteration, we will always be less than or equal to this value. So basically all I did is I just said A is equal to xi, h is equal to negative nabla times the gradient. Okay, this is still a little bit of an ugly looking function. So what we'll do is we'll just do a little bit of factoring here. And what we'll find is this will be the same as the following equation. That's just factoring. These two are completely equivalent to each other. So now you guys may be asking, how does this prove that we're going to be always making progress? All you've just done some factoring stuff and we don't really see it right now. But what we're going to first say is we're squaring a value here. So this value is always positive. And now we have like some constant factor here. And so if we have a value and we're subtracting a positive value from it, that means we will be reducing our value and therefore making progress. But that is dependent on this term not being negative, right? So this is conditioned on the fact that following term needs to be greater than 0. And so if you recall, when I said we have to choose our step size carefully, what we're going to have is we need to have, let's see. We should be less than 2 by, oh my God, the handwriting. Right, so basically, as long as we choose a step size that is less than 2 by beta, we will converge. We will make progress. That is why we say the step size is very important. Because even if we have a really nice function that's smooth, if our n value is greater than this, we cannot guarantee that you will always make progress. And therefore, you may not converge ever. Okay. Any questions so far on step size, smoothness of functions, stuff like that? Yeah.
So this beta corresponds to the model that we defined.
Yes.
Of the loss function.
Yeah.
And as for the pictures, the 3D picture you showed, they are not so valid loss function.
Yeah, so those are not nice loss functions.
Okay.
Those are just loss functions given as an example to motivate gradient descent without saying like we have a picture perfect function.
So in reality, we always use models that.
No, we don't. We unfortunately do not get that luxury always because certain loss functions are just, they're not well suited for certain models. What we'll find is the loss function that we initially started with and like most of ML theory is based on is a minus b squared, the mean square error function, because of this. But recently, the loss functions we deal with are not differentiable, or they're very hard to have these bounds for. But there's an interesting correlation between the two because it proves that gradient descent actually still performs very well, even if we don't have these criteria. That proof is very involved. There are a couple of research papers for proofs based on that stuff. So if you guys would like those, I can send them to you. But it is well out of the scope, and I've never looked at anything like that before either. So, yeah. Any other questions so far? All right, cool. So that is your first machine learning proof kind of done. You have proved that gradient descent will always make progress. So now if you ever take an ML class and like, oh, does gradient descent always make progress? Yeah, if you have a beta smooth function, it will make progress. So yeah, that's a bit of the theory there. But now we're going to talk about one last thing, which answers the question about having multiple local minimums. We're going to talk about something called the convex function. And convex functions are really nice because all they say is if you have 2 points and you draw a line between these 2 points, it'll always be above the curve, right? For example, x squared, you can say any 2 points, and if you draw the line, that line will be above the curve at all times. And why do we like convex functions? Because the local minimum is the global minimum. So that means we have exactly one optimal solution that we can shoot for. And recall our lovely loss function a minus b equals a minus b squared is convex. And that means if we find the right solution, this is the one and only solution for our problem. Okay. Yeah. we won't get into the math definitions of convex functions because we won't need that. But basically, the large theorem for most of gradient descent proofs relies on this. If you have beta smooth and convex function, we can say that within a certain number of iterations, we will be within a margin to the optimal solution. So let me just write that out. So K here is the number of iterations we're going to run for. This is our starting point. This is the optimal solution. So this is just calculating the distance between our starting point to the optimal solution. One question that'll come up is, oh, what if we don't know this optimal solution? This is generally just a constant factor. So this is just like a constant factor that we're multiplying by. It doesn't change anything. Beta is the smoothness factor that we were talking about. And 2 times epsilon. Epsilon is the difference between our final value and the optimal value. So if you want to guarantee that the difference between your optimal value and your final value is within 1, you will need to run between 1. You'll have to run 1 over epsilon iterations to get there. Is basically what this is saying. So for example, if you need to get within 0.1 of something, you have to run 1 over 0.1, which is around 10 iterations. Of course, multiplied by some constant factor here. Okay, so this is the big theorem. And this is really nice for us, right? Because now we can say that we will find a solution within a certain amount of time. And gradient descent does actually work for something. It's not just this greedy algorithm where we cannot prove it won't work for something. For those of you interested in the proof, I have it right here. So after, you guys are welcome to read through it. You do need to know about telescoping sums and stuff like that. So if you're interested, you guys are welcome to read through it. And if we have time at the end, I can also write it out, but I don't think we will. There was a plan to initially write it, so there are about 8 slides because the proof is about 2 pages long. Reasons why we're not doing the proof right now. Okay, so now the question comes into, okay, gradient descent, it works. Great. But this entire time we've kind of made these assumptions and we're like, oh, but you know, it can be fairly slow. So are there any ways we can make gradient descent better? How do we make it faster? And we're going to take some intuition from physics. And so let's go back a little bit and we'll think about the idea of a ball rolling down a hill. That's basically what gradient descent is doing, right? We have some object and, you know, it'll keep moving where gravity is pushing it down, right? Which is the steepest descent. And then you'll reach a local minimum and it'll just kind of roll there and it'll settle and you'll find your local minimum. But in gradient descent, we're taking this constant fixed step, right? It's not really like gravity where the force is compounding on it and it's not moving faster, but it's just moving at a constant rate. So in theory, if we were to think about the idea of physics, where we have compounding momentum, we should be able to converge faster for gradient descent, right? So basically what that's saying is when you take a step in one direction, your next step will be influenced by your previous step, the magnitude of your previous step. So as an example, if we have something like this, and we have a ball rolling down, we want to use gravity. So basically we want to make it go faster as more time progresses. We can increase our step sizes as time goes forward, because we don't really need to be taking the same step size. If we know the direction we're going in, we can just increase our speed. And so that's the idea. It's literally just momentum is what's happening here. We add momentum. So what is momentum in gradient descent? It is basically we're keeping track of the previous magnitudes of our step sizes, and then we're using those to influence our future steps, right? So let's say we were traveling in one direction for a really long time, and then suddenly our gradient gives us something really weird. We won't listen to it as much. We are going to still have some movement in that same direction. And that'll allow us to converge faster. Same thing about like a ball rolling down a hill. So how does that look? That will look like something like this. So this is your standard gradient update right here. But you'll notice instead of saying the gradient at this point, there's this new term g of I. And g of I is defined as follows. And so basically what that's saying is you take your previous v value, which is the previous step you've taken, that momentum, you weight it with some factor, and then you also weight your current gradient with some factor. You compose those two and you take a step in that direction, right? So if both of these kind of align with each other, if the gradient xi and your previous gradient are aligning with each other, you're going to take a farther step, right? You're basically doing 2 times alpha. Okay, so this is called NAGD. It's called Nesterov's accelerated gradient descent. And so that's just basically the entire idea of momentum. And what we have for momentum is this nice little NAGD theorem here, which says we converge in this number of iterations compared to 0.1. So basically we're saying we're going to converge much faster compared to the regular gradient descent. Okay. Then now that we kind of have an idea of gradient descent, momentum, we can talk about the big thing, optimizers. And so optimizers are things that you will use in PyTorch and stuff like that, where you see like, oh, optimizer, choose atom. That's like the default one. We're actually going to talk about mathematically what happens with atom at a high level. So to understand atom, we're first going to start with something called adaptive learning rates. Okay. So if we have a lot of oscillations in our gradient, we don't like those gradients, right? Because they're going to be bringing us in different directions. And if we constantly keep moving in one direction and we're not sticking to that, we're not going to make progress at all. So basically, what adaptive learning rates do is we look at the change in the gradient with respect to each coordinate. So remember, your gradient is a vector, and you have the change with respect to x1, x2, and so on and so on. And so we will weight each of these coordinates with a different step size and a different value. So if x1 is not oscillating that much and it's making good progress, we will give it a higher weighting. We will want to take larger steps in that direction. Suppose x2 is being obnoxious and doesn't want to cooperate with us and is being, annoying. We won't weight it as much. We'll kind of ignore it. And so adaptive learning rates basically relies on the idea that oscillations are bad and we want to take bigger steps along directions where the gradient is more steep. Any questions so far about adaptive learning rates? Yeah. So basically what I mean by oscillations is, for example, if I have a gradient that is moving in this direction and then now in this direction, and maybe now in this direction, and back up here, these are oscillations. We don't like this, right? Because you can imagine that there's probably a nicer path that can come straight through if we end up right here. So it would be much faster for us to weight certain of these weights so that maybe our paths kind of look something a little bit more like this, closer to this optimal line. And so that's what I mean by oscillations, where the direction of the gradients are just changing. Any other questions? Okay. Now we can get into atom. And so atom is a combination of something called RMS prop and Nesterov's accelerated gradient descent. So RMS prop relies on adaptive learning rates. So you can think of those two as synonymous. And we just talked about Nesterov's accelerated gradient descent. We're using momentum, right? So we're kind of trying to go faster as our iterations progress forward. So that is basically atom. You're taking adaptive learning rates, so you're weighting the different directions differently, and then you're also compounding these weights together. So that is the optimizer that's heavily used right now. So that's like the tidbit for like the practical side of things. Okay. Now we get into going into why gradient descent sucks and why gradient descent and Nesterov's accelerated gradient descent are not used in practice almost ever. So basically, if we take the following function or the loss function, for each gradient set, we need to compute this value. This value is very annoying to compute, right? So if we say that we have an n by d matrix, an n-dimensional n by d matrix, to compute this takes O of nd time. Basically what we're saying is we will have to run this for this many iterations to compute this value. And then we are going to have to compute the gradient. Now, ND, for those of you who maybe done CS32, doesn't sound too bad. It's just O of n squared. But our number of samples, as we said in the beginning, can be in the millions or even billions. So this value, even though it's O of n squared, you can think of it as like maybe a billion squared per iteration. That's the most important thing. This is not just like, oh, 1 billion squared and you get your final answer. No, this is one step. You're doing all this computation for exactly one step. That's awful. We don't have time for that. You will probably not be alive by the time something like that finishes running if we keep doing something like that. And so one example is if you have a data set of 1 million images and they're 250 5 pixels by 250 pixels by 250 pixels, the time complexity for one iteration is this. This should be a 250. That's the amount of time it's going to take for this algorithm to run, multiplied by how much ever time it takes the computer to perform that operation. And you will have to repeat this, as you said, 1 over epsilon times, right? Because you want to get an accurate result. So that's not great. Now, some of you may have heard that some of these machine learning problems have something called a closed form solution, which means we don't need to run any algorithms to get the right answer. There's just a mathematical formula that gets the right answer. And for this one, what we'll actually have is this. You don't need to worry about what this means, but basically, if you take x transpose, multiply by x, invert it, multiply by x transpose again, and multiply by y, you magically get the right answer. We calculated that by taking the gradient of the loss function, but you don't need to worry about that. So great, problem solved. Not exactly. Computing the inverse of a matrix takes cubic time. So we were kind of worried about quadratic time, and our optimal solution now requires cubic time. So what we're going to see is even the closed form solutions are not feasible to compute for very large data sets. So now we're kind of back in the area of, man, we just have to deal with gradient descent. It's probably the fastest thing we got for now. So that's going to be the next issue we're going to try and solve here with gradient descent and optimization. And that leads us to something called stochastic gradient descent and mini-batch gradient descent. So what was our biggest issue with gradient descent? We have to do this for every sample in our data set at every iteration. So what's an easy way to just let that go? You only do it for one sample, and you assume that's true for the entire data set. So now your time complexity is only going to be O of D, right? You're only doing it for one sample. But everything comes with a cost here. What happens if you only take the gradient of one sample? Does anybody have any ideas why that may not be a good idea? You do have to take more steps, but remember that when we're computing the gradient across all of these different values, we're accounting for how our function needs to change with respect to all of the parameters. So suppose your data set has an outlier, and you happen to pick that one outlier. Your gradient set will just lead you in the wrong direction then, and you're screwed. That's even worse. So maybe there's some sort of compromise between choosing just one sample, choosing all of the samples. Anybody have any idea what that compromise may be? I heard something over there. Choose some of the samples. Mini batches. You choose a batch of samples, you calculate the gradient on that batch, and then you move in that direction. So instead of O of MD, you get ND, you get O of MD, and M is your batch size. And note, when you have 1 million and you choose like a batch size of like 20, significant computational decrease right there. So that is basically stochastic gradient descent and mini batch gradient descent. Instead of doing gradient descent across all of our samples, we assume that if we take like a certain set of samples, we randomly sample like 20 samples each iteration, we compute the gradient just on those, we'll still kind of hopefully converge. Now, the reason we kind of talked about the proofs of gradient descent initially is that the proof that randomly sampling samples will give you the optimal solution is not clearly apparent. But basically what we get is that if you take the expectation of this, the expectation of stochastic gradient, the convergence of stochastic gradient descent is equal to the expectation of the convergence of gradient descent. So that was a bunch of jargon. This is how you can think of it. expectation is like something, it's basically like some probability that you'll actually end up in your result. What we're saying is with a certain expectation, so with a very high probability, as long as we're sampling randomly, stochastic gradient descent and mini batch gradient descent will still converge. There's also a proof written up for that. If you want to look at that, you're welcome to, but you do need to understand expectation for that one. And
Sorry, can I take again?
yes, so this is a really, don't ever write this. Okay, this is just for like purely illustrative purposes, and basically what it's saying is the proof that mini batch gradient descent will actually converge is just taking the proof of gradient descent and putting an expectation symbol in front of everything. Okay, and that is the entire proof. There are like one or two like twists there that will cause some differences, but they're very minor.
On a
But-
high level, this means we're hoping that when we take mini batches, it is going to be a good enough approximation of what our gradient would be calculating if we were to say take the entire data set. It's not gonna be exactly, but we're hoping that as we take more steps, it's gonna eventually be about the same thing.
Yes. Okay, any questions about SGD, NAGD, gradient descent, proofs? Do you all want to see more proofs? Would you guys like me to write out the 2-page proof for gradient descent?
Yes.
Yeah.
Yes.
I mean, show of hands, like I'll do it. I have it printed out, so like, I came prepared, guys.
Will these materials be available after?
Yeah, we
Yeah, I'll post my notes. I'll post the ones that are actually properly written. Don't worry. Is that a yes?
That's it.
I see. Okay, you know what? If we have time at the end, I'll let other people leave who don't want to look at the math anymore. And then people want to see the math, I can do that then. Okay. Now we get into the fun stuff and like a little bit more of the practical stuff. Still a bit of math, but we can talk about constraint optimization. And this is personally my favorite thing to talk about, because I just think it's so cool. So in all of this, we're assuming that we can choose any real value. And that's not always true. So I gave this really bad example to somebody, and I can't think of another example to give, so I'm going to give you guys the same really bad example. But if you take a function of your overall well-being with regards to your happiness, bear with me, would you negatively weight your happiness? I hope that in no situation would you weight your happiness as like a negative factor to your well-being. I understand that was an awful example, but we don't want negative values, but we don't want certain values sometimes, right? For example, if you're dealing with maybe like, let's say dollars, you don't want a 64-bit floating point integer. It just doesn't mean anything to you. So we're gonna have to deal with constraint optimization. We have constraints on our possible values, right? And so, yeah, that's the happiness example. That's like the relationship to constraint optimization. And what we'll actually find is most of the machine learning settings actually deal with constraint optimization. And the real reason for that is we want our models to have something called semantic meaning. And so you could have a model that will minimize your loss and negatively weight your happiness. But a model like that just doesn't seem to make sense to us. It's like saying if you have a bunch of healthy cells in your body, you're like subtracting that when you have a machine learning model that'll tell you if you have like a certain type of disease or something like that. Things like that just don't make sense, even if they may minimize our error. And what does that mean? We're not really generalizing well, right? The point of machine learning is how do we get to a point where we have like human level cognition and human level learning. So we want it to have semantic meaning. And basically by putting these constraints is one way for us to get semantic meaning into these models, right? By saying, hey, your happiness is important. It's not a bad thing. And so that's why constraint optimization happens a lot. It provides your models with more semantic meaning. And so how do we kind of deal with that? We have another form of gradient descent. So many forms out there. This one is called projected gradient descent. Projected gradient descent is probably the easiest gradient descent to understand so far because it does what it says. It's just gradient descent, but every time, let's say this is your set of like parameters. You're over here. Take a step out. So now you're in violation of your parameters. You just step back into the closest point right here. and then you continue optimizing. You step out, you just step back in. Mathematically speaking, we're just taking projections. And so if you did linear algebra, we're just taking a projection each time. And so the formal algorithm for that is over here. Oh boy. Okay. That's off the place, right? XI projection. Okay. Standard gradient update, projected back into your set. Projected gradient descent. C is the set of is the set of your parameters that you're actually allowing to, right? So that's the notation there. So projected gradient descent is actually very heavily used in current machine learning research, and we'll get into that in just a few minutes. Why it's like so cool, why it's really important right now as well. But one thing I do want to say is because this is supposed to be theory track, there is a proof that projected gradient descent works on convex sets. So all those statements I said about gradient descent, natural accelerated gradient descent, and stochastic gradient descent all work for projected gradient descent if you're dealing with a convex set. What is a convex set? If you have a circle, you take any 2 points within your set, you draw a line segment between those 2 points, the line segment is within your set. Okay, so as an example, the circle is a convex set because I can take any 2 points with this. If I draw a line that's within it, these points will always be there. And so if I were to just give you like a 2-dimensional example here, let's say, let's say this is my set of all allowable parameters. Somebody decided that this provides our model semantic meaning. All your biases, all your weights have to be within here. This is a non-convex set, right? Because if I take a point over here and a point over here, I draw a line segment, that line is not within our set. And so then all of our proofs crumble, fall, and fail, and we're sad in theory. Practice, we're happy still. But theory loves convex sets. Okay. That is projected gradient descent kind of rushed. Okay, now onto the tangents. So how many of you have heard of adversarial attacks against machine learning models? By show of hands. 1, 2. So a few of you. Basically, what an adversarial attack does is I give you an image of a pig, I add some noise to it, and now the ML model thinks this is an airliner with 99% certainty. And this is actually the image with the noise added. If you look on the slides, they're posted, you can barely tell the difference. This is still a pig. Us humans can tell that this is a pig. So this seems pretty bad. I can add some noise and suddenly our entire model is failing. Why is that? Well, that comes back to the entire idea of having semantic meanings. Our model is clearly not looking at the semantic meaning of a pig. It's just weighting some random pixels, and suddenly when we add noise that affects those pixels, it thinks it's an airliner. Okay? So, how do we construct an adversarial attack? Is going to be the next part that I'm going to talk about. If you guys have the means to do this, great. Don't do it on Tesla, please, because we will get sued then. So don't do this on stop signs. No shady stuff. If you're interested in that stuff, they actually have research about that too. So join a lab and then do shady stuff like that. As Jordan can attest, labs are great places to do shady things.
I will not confirm or deny that.
I will confirm that. Can we cut that out? But basically, how is the noise computed? So when we're thinking about this problem, we want to figure out what this noise is. And we want to add this noise to an existing image, but keep the existing image within a certain bound, right? Like, obviously, if I made this pig, I added a bunch of noise and made it look like an airplane, that's not an adversarial attack. That doesn't give us any fun or anything good to do, or bad to do, rather. So what we're actually doing is, this is a constrained optimization problem, whether you realize it now or not. This circle, we'll say, is the set of pig images. The first pig image we had is maybe somewhere over here. What we are trying to do is we are trying to add some amount of noise so that we get to a different image of a pig within this set that now gets classified as an airliner. And so instead of minimizing something, we are now trying to maximize our error. And that is something called steepest descent. Most people in the ML community will still call it gradient descent, because you just multiply by a negative number and it does the same thing. Okay, so basically why projected gradient descent is so important is this set of pig images, we have to stay within. Because otherwise I can add so much noise that it's not even going to be a pig anymore. So if you ever want to compute an adversarial example, you take a pre-existing image of a pig, you add some random noise to it, and you apply projected gradient descent. So that every time you add too much noise, you step back into a threshold where your noise is okay, and it still looks like a pig. And this stuff is a current area of like research and how you defend against stuff like that. Jordan.
And in practice, what that means is, okay, so just a quick thing. When we're normally doing gradient descent to train a model, what we're doing is we're saying, okay, we have this model. We want to see how we can push the weights around so that we're minimizing the loss, right? Because that means that our model is performing well. However, what we're doing here is we're saying we're taking the gradient with respect to the input image itself. AKA, how do we push this image around so that the model does poorly on it, so that the model thinks the image is an airline. And specifically, in practice, what we mean when we say apply projected gradient descent on the pig image is if we were to say calculate this gradient with respect to the image, and there's this one point where the gradient is really, really large. So when we add the noise onto the pig, it will be like every other area is like, you can't even tell it's different. So there's this one area of pixels super duper bright because that's what the gradient happens to be. We just clip it. We clip it to, we say the gradients, all values in the gradient has to be smaller than say 1/25th of the total brightness of the image or something like that. We can make constraints like that depending on what we consider as this is still a pig image. And by doing so, we are able to say, oh, we can keep doing gradient descent to try to make the model really confused while still staying within the constraint of this looks like a normal pig image, if that makes any sense. Does that make sense? Okay, cool.
And if you're interested in the research of how you determine the constraints, there's something called the L infinity norm or the L ball norm. And you can look into that wild stuff in that area of research. But that is adversarial attacks. And so gradient descent is applied adversarially to negatively affect models. Yeah.
I think this kind of requires like the attacker is to know like how the model like predict this picture, like how much percentage is pig and how much percent. So that is normally inaccessible.
Yes. So you are right in the statement that you need access to the model.
Statistics 5.
It makes it significantly easier if you know the architecture of the model. Basically, like what are the weights? How is it weighting things? But it has actually been proven that you can still apply this when you don't know anything about the model itself. So if you treat the model as a black box, as long as you have unlimited access to this model, you can feed it in an input, and as long as you note down its output, you can still do this attack. You don't need to know anything about the model. You just need to have access to it and say, I can give it an input and I can get an output from it. And there's actually a research paper about that. So it's not just enough to say, oh, I know that this is a convolutional neural network with this many layers, et cetera, et cetera. These attacks, unfortunately, still can happen.
So even if with a model that only tells you, I think this is a big, but you do not know my confidence level.
Yeah. We can still do that. So I can send you the research paper for that. That is a lot more math that I actually don't know. So, but that is a projected gradient descent and kind of the fun stuff. Oops, of that. All right. So for your guys' sake, if you guys are interested in more like optimization theory stuff, a couple classes I can recommend. CS260B proves all of these, and then there's a ECE course for convex optimization, which is also very good if you want to do machine learning research. So those two. But then kind of some things to keep in mind. Some of the proofs we've written kind of make it seem that gradient descent is like solved and like this is like the optimal stuff, but that's really not the case. So far, if you were observant, all of our proofs are based on L2 norms, so Euclidean distance norms. That is not necessarily the best norm to use. So if you've heard of things like graph learning and graph modeling, there's actually a different set of norms you would like to use that will give you even better results than using L2 norms. Then these are like the practical tricks that are actually used in practice. One of them is called gradient clipping. We talked about adaptive learning rates, and that is used to make stochastic gradient descent and gradient descent more practically applicable. There's also something called mirror gradient descent. And basically what that does is it changes a bunch of your variables to make your loss function nicer to optimize. So those are like some practical things that you guys can explore. But that is kind of all of optimization. And this is all the optimization theory you should ever need to know for like anything you do, if not more as well. Any questions on optimization theory before we get into neural networks? Cool. All right, so now we get to talk about neural networks and forward propagation. And you want to do this, Sparsh? Yeah. And Sparsh will do this portion. Do you want the iPad?
Right. Right. Okay. So far we've been talking about the parameters of our. Thank you. So far we've been talking about the parameters theta, right, of our model, and we're trying to modify theta such that we can make everything optimal. But we haven't really discussed like what theta means in like a practical sense, other than this sort of abstract set of parameters. So this is like a simple example of one possible architecture we could use, and we'll go over like what exactly like the theta would be in this context of simple, just typical fully connected neural network. So we'll talk about that in the context of forward propagation. So the idea is that each of these okay. So the idea is that each of these layers is a vector. So you have this as the input layer vector, then it gets multiplied by some weight matrix to then produce the next vector in our model. So we can represent that as x. So this is sort of the equation that we're going to be building up to. So when you see each of these connections, what we really are referring to is this as the sort of linking process that takes you from one layer to the next to finally the output layer. So first, we'll just look at that weight matrix itself. The idea is that for every single neuron in the previous layer, it should be multiplied by a corresponding weight. And then you take that for every single neuron in the layer, all of them multiplied by their own corresponding weights. You sum those together, and that provides you with the first neuron in your next layer. And you do the same thing for the next neuron in your next layer, the other neuron in the next layer, all the way down to the next one. So what that ends up looking like is sort of a matrix product, where you have your input vector, and then you have it multiplied by a weight matrix. And that will produce like a vector that is of the size of your next output layer. So that would be this equation here. So in order to make it so that our model isn't just necessarily constricted to starting at the origin all the time, we can have a bias as well. So that way we can move it up and down through the output space that defines our second layer. And that allows our model to capture a little bit more complexity. And so we end up with effectively this as a sort of illustration of what's going on. And this is the model that we end up with. So this is sort of the central sort of equation just of when you're talking about linear equations, right? You just see this. This is the quintessential linear equation. So far what we've built up to is we have a bunch of layers, one connected to the next, and you do a linear transformation to get from one layer to the next layer, so a linear transformation from that layer to get to the next one, and so on until we get to the output. Now, the goal of adding the subsequent layers, right, is to allow our model to model more complex things. But on that front of modeling complex things, does anyone notice a problem if you just keep having a linear layer after a linear layer after a linear layer? So the problem with this is that every single time, because of just what the properties of linear equations are, if you have one linear transformation and then you apply the linear transformation to that, you end up with another linear transformation, right? Because if you multiply this out, and you'll end up with x being multiplied by some other weight matrix plus some other bias vectors. That's not any of these three, but you'll still end up with something of the form w times our input vector plus b. So the way that we have it currently set up, our model can't actually get any more complexity by adding extra layers because everything is linear. And so it's meaningless to add more layers because it's the same thing as just having one. So the way we solve that is simple, really, I guess. It's just make it not linear. So that's what this little sigma sign is. It just means it's a non-linearity function. So that's the solution. So this sigma can be like a whole bunch of different things. The only important thing is that it's not linear. But you could have something like the you could have some function that looks like this, which is called the sigmoid function. And then you could have another function that's used quite often, which is called ReLU, which looks something like this. So these are like two possibilities of non-linearity functions. And the idea here is that, I mean, obviously for the sigmoid function, you can see the curve makes it non-linear. And for ReLU, the idea is that if you just chop off the negative side, this introduces this little non-linearity, and that is sufficient to model a lot of complexity. And actually what we find is that ReLU tends to work really well as a non-linearity function because it has a really simple derivative, and it doesn't have this problem that it sort of flattens out the way the sigmoid does. Yeah. So these are just some examples, right? There are other things, as I mentioned, ReLU. You can even use like floating point approximations as a source of nonlinearity. As long as something is making it nonlinear, then you end up with more complexity from one layer to the next. Another type of function that we use quite often is called the softmax function, which will basically take any vector and sort of normalize it so that you end up reflecting probabilities. And this is useful for output layers, right? Like if you have a bunch of classes like an output, like this, where you say there's maybe an 80% chance that an image is a dog, maybe a 10% chance that it's an airliner, maybe a 5% chance that it's a pig, and so on. And so that way, if you have all of these just as numbers that add to one, what you find is that you can model this as a probability, and that makes a lot of sense, like in a sort of human semantic context. Yeah. So that's really it as far as feed-forward networks, as far as neural networks are concerned. So when we talk about optimizing the theta parameters that we were talking about, what we're really trying to optimize here are the weights and biases that define these connections. And that's one example. In different architectures, you'll find that there are different things that you're trying to optimize. In this situation, we're trying to optimize the weights and biases from one layer to the next. And yeah, that's all of it. So if you guys have time, you can fill out this.
If you scroll down a little bit more,
and
we have a better version of feedback.
yeah, okay, there we go. Yeah, so that's about it. Thank you for coming out to the theory track today. And I'll hand it off to Venkat.
Yeah, so that's the end of theory track. Thank you all for coming out. So we do have 40 minutes. And as promised, that means for those of you who want, I will write the proof out. But yeah, you guys are welcome to go because the proof is just.
And before Venkat does that, I have a really quick announcement about just ACM in general. So this Saturday, for some of you who may know, who came to Apply Track, you know that we have reading groups on some of the Saturdays at E6289 from 12 to 2 p.m. This Saturday, we actually have a pretty exciting reading group where, have you guys heard of Stable Diffusion and AI art and stuff like that? It seems a nod, right? So the company, which is Stability AI, and the reason why they're relatively well known because they're one of the few companies who completely open source every single one of their AI or text to image models they've done. And one of their more recent models is stable video diffusion, where you can do text to video generation. So and that effectively allows you to also do the text to video generation, right? And one of the co-authors of that paper, who was also used by students, is actually coming to our reading group to talk about how stable video diffusion was built, the current state of the diffusion model, video diffusion model kind of landscape, and where he thinks the future is going for generative video. So if you are interested in that, feel free to come to this Wednesday at E6 at 289. But if you're in our Discord, we will also announce this. If you're subscribed to the CS newsletter, if you're CS major, then you will see that. It's also going to be posted on Instagram relatively soon. So just a quick announcement regarding that. Now back to Venkat.
Okay. I gave you guys the like visual description of convex functions, and to do the proof, we need the
Reminder that applied practice this Wednesday if you want to keep working on your projects.
Can you repeat the question?
question.
Like,
I'll start with. We'll let everybody clear out.
Where'd you go with that?
Wait, I don't want to break it. Go ahead and get it down. You can like use it as like a teaching tool. Okay, no, I probably won't use it. Okay. Wow, a lot of people want to stick around for the math. Okay. Hopefully you guys still want to stick around after this. But so I just gave you guys the visual definition of a convex function. It's like, oh, just draw a line. It's all good, guys. I don't know how you guys thought about that in n dimensions. So this is the definition of a convex function. Okay. Evaluate your initial point, take the gradient at that point. You multiply by the difference between the second point, and that should always be less than or equal to the actual function value at your second point. That's just the pure definition of a convex function. And okay, so now we can get into proving the bound for gradient descent. So let me, because we have time, I will be a little slower and I will actually write out the full theorem in like a mathematical notation. You guys will get the true theory track experience. So we say, let f be a function defined from an r-dimensional space composed of real numbers to r. We must have that f is beta smooth and convex. This proof will not work otherwise.
Aren't convex functions beta smooth by default?
Not necessarily.
Okay.
What is beta smooth again?
Ugh.
Long ago.
Beta smoothness is, wow, my notes are really messy, guys. I'm so sorry. This thing,
It's smooth, basically.
it's nice and smooth. You're basically saying that your gradient is changing with respect to the difference between your points, like the Euclidean difference between your points, not like the valuation of the function, but just x and y.
Oh,
That was a 131.8.
So Jordan just mentioned something else called Lipschitzness, which is a different metric, and it is in these notes. Lipschitzness is not used in this proof because this proof is nicer to do. The Lipschitzness proof is awful. And there's a theorem. So if you guys are interested in Lipschitzness, look at the proof. It's all written in here. So yeah, and basically you, just like we say a function is beta smooth like Q smooth, we just say a function is L Lipschitz. So you can say a function is 2 Lipschitz. It's pretty fun to say, but it wears on after some time. But this is beta smoothness. And basically, the only reason we care about beta smoothness is so that we have the first gradient descent proof saying that we'll always make progress. Because we'll actually end up using that.
Can you think of cases where a function is convex but it's not beta smooth?
Big draw.
Let me think. Ah, yes. I can just draw it right here. if I gave you a function that looks something like this. I hope nobody defines like, because of this,
Not different.
not differential, and this is not a smooth function. So like this will generalize to like higher dimensional cases as well. There's probably a better example. I will search it up. I can't come up with something off the top of my head besides that one.
If you have a cubic function, how do you calculate the beta value for it? Because that doesn't, the derivative isn't a constant there.
Yes, so not all cubic functions are beta smooth. By definition, if you have like a cubic term, your rate of change in your gradient is not going to be proportional just to the absolute difference between the values. So it's not beta smooth.
So any higher degree polynomial.
Any higher degree polynomial will not be beta smooth. Okay. So let's go ahead and write this. So f is beta smooth and convex. Given that our step size is less than or equal to 1 over beta. So if you recall, we said that our step size has to be less than or equal to 2 over beta. 1 over beta is constant factors. We can ignore them. And what we're saying is we will get the following theorem after, or we'll get the following information after k iterations. So the function at the kth iteration. So our x value on the kth iteration will always be less than or equal to the optimal value. So x star is some optimal value plus the difference between our starting point and the optimal solution. So the norm between those two, and 2 times the number of iterations. Okay. So this is the theorem we're going to try and prove. And basically what this is saying is, if we just want this to be within a difference, I rewrote this formula for you guys when we were talking about it, so it's easier to see that you would have to run it with respect to the difference that you want. But k here is the number of iterations, and we'll get into all of that. There is one other thing I forgot to mention while everybody else was here, but somebody asked a question about how do we choose the starting point? And so the starting point is chosen randomly in gradient descent. So in practical applications, you've got to have a little bit of luck. But of course, when we're dealing with a convex function where there's exactly one optimal solution, our starting point being random doesn't matter. If you guys are in practice, something else called simulated annealing can also be done to find an optimal solution with multiple random starting points as well. Okay, so this is the theorem that we're going to try and prove. So we're going to start off with two things that we already know. So this one is by smoothness. So we have so this is another property of a function being beta smooth. For everybody's information. This is just like a definition. That's why we want it to be beta smooth. And the
Where is beta?
beta does not appear here quite yet. Well, this is something, so if you recall in the theorem definition, we say n is less than or equal to 1 over beta. And so basically you can take this to be 1 by 2 beta. And we can say n equals 1 over beta, if that makes things clear. So that's why there's no beta quite yet. We'll substitute that in later in the proof. And then the thing that's given by convexity is the red definition that I decided to gloss over. And basically what I've done here is x star here denotes the optimal solution. Okay. So what I'm saying is at our starting point, our starting point plus this difference, our optimal solution will not be farther away from that. Or it'll always be farther away from that. Okay. Okay. So these are our first two functions. The first step in this proof is that we are going to add these two functions together. And so what we're going to get is we are going to get this. For the, by the way, these two like single brackets are like the dot product, by the way. And that will get rid of like later in the proof. And just for a lack of space, I'm writing it on 2 lines here, so hopefully that's not too confusing for everybody. Okay, so I just added equation 1 and equation 2 together, and you get this. And so now we're gonna do some algebraic simplification for a bit. First thing we can do is we'll knock off the xi's. You can just subtract it, and they cancel each other out. Okay. So what we then have is this. So I just rewrote the same thing without that with x's. So far, so good. Okay. So we haven't actually used anything about gradient descent yet, right? This is just a property about your function is beta smooth and your function is convex. You can get here. But now what we know from gradient descent is we have the following. Before I do that, I will actually rewrite this. This is just, I'm going to move over these 2 terms to be on the same side. And so then what we're going to have is we'll have this. Any questions so far with the algebraic manipulation that went on here? We're just going to say the difference between our ith iteration and the optimal solution will be less than or equal to this. So we're saying our difference is within this margin. Okay. So then we're going to recall the gradient update step. So what is that? We say x of I plus 1 is equal to x sub I minus this jazz. Yep.
So I think we can make sure that the left side is always positive, right?
Yes.
Then on the right side, we have to make sure the first term is much more positive than the second term. And in the 1D case, if x star and xi are both scalar, how can we make sure?
So actually, we want this term to be more negative than
Yes,
this
more
term.
negative. Yeah, I include the negative sign.
Yeah. So basically, what we're trying to say is that this should be a very negative value. The gradient should be.
But that depends on whether the second one is. Yeah, I think that's.
So this is the gradient update. And so what we are going to do is we are going to express the gradient in terms of the I plus 1 and the I to x value we had. So what we get is this value, xi minus c plus I n. So yeah, hopefully we're all good with this. And naturally, what we're going to do is we're going to substitute it into this wherever we see the gradient symbol. So what we have here is this will now be xi minus xi plus 1 alpha Any questions so far? So what we just did is we basically used our gradient update rule so that we no longer have to deal with any gradients. So if you look at this now, everything is now in terms of a single point. We're not calculating b gradients at any point right now. Everything is just in terms of a point I and the next point I plus 1. Okay. So with a little bit of algebraic manipulation, what we'll get is we'll get something that will look like this. So any questions on the algebraic manipulation that went on here? I just put this 1 over n outside, and I brought this negative sign into this term. And then over here, this is just going to be 1 over nobla squared. So you get negative 1 over 2 nobla. So far, so good? All right. So now we're going to do a little bit more algebraic manipulation so we get it into a nice linear algebra theorem, actually, that we can apply. So right here, I'm going to stop writing the left-hand side for a bit. If that's okay with you all. So this left-hand side is going to just stay constant. Okay. And let me know if this algebraic manipulation does not make sense, and we can go over it. Does everybody get how we went from this to this? Minus 2.
On the solid basis. Yes, there's a the two. That's
Oh.
two.
That's numbers. Thank you. Are we all good with how we got here?
What is it, the two subscript meaning?
This is basically, so this 2 norm right here means we're using the Euclidean distance. So it's just your Euclidean distance formula. There are like different types of norms that will do different things, but we're using the L2 norm here. So the reason that I wanted to have this extra 2 here is, if you recall from your linear algebra class, what we'll actually have is that if you have something of the form 2u, using these. This is equal to. All of these are in L2 norms, by the way. In case I forget to write 2 norm blocks. This is from linear algebra. And so now we're going to expand this out. And what we have is we're going to have xi plus 1. Everybody get how we just applied this formula just to this term, right? So u here is xi plus 1 minus xi, z here is x star minus x. So far, so good. Any questions so far? Okay, cool. Then if we look at this, what we'll notice is these 2 terms are going to cancel each other out, right? So the easy way to see this is if I factor out a -1 from this, it's going to be the same thing. So we have -1 times this expression, and because this is squared, the -1 does not matter. So these 2 are the same exact thing. So we can just cancel them out right now. Okay. So now what we actually get is something of the form . So I just canceled these two terms out and I'm left with x star minus xi and xi plus 1 minus x star. And these two are again the same thing. They're equivalent to each other because it's a -1 trick that we can do. Okay. So now we get into the telescoping sum portion. And we're going to start writing out a couple iterations. So we'll start off with x1. So this is why I had so many slides. Okay. So we start off with I equals 0. We're going to have f of x1 minus f of x star is less than or equal to this. Right? Does that make sense? We just substitute I equals 0 here. Okay. Now we're going to go and do this for I equals 1. We're going to get the same thing, but instead of 1s and 0s, we're going to have 1s and 2s. So this is going to be a 2. This is going to be a 1. And this is going to be a 2. Now, if I write this out for the kth iteration, what is that going to look like? We're going on to the next page now. Oh boy. Okay. So now if we think about this, what happens if we add all of these inequalities up with each other? Does anybody see anything like nice happening? Like, okay, so let's say we just added these two lines together. Does anything cancel out for us in these two lines on the right hand side? Anybody see anything that cancels each other out? Any idea? Yes, sorry.
So if you, like, for example, if you take the first two, the term on the right squared and the term on the left, the second one, they cancel out. And if you keep doing it, I think you only do that for the first and the very last.
Exactly. So basically, if we add these two together, what we're going to have is we get something of the form. Oh, that's the wrong one. So I'm just going to write out the left-hand side as well. This is going to be our left-hand side. Plus dot, 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 up till our k value. So we understand we're just adding everything on the left-hand side together here. Now, on the right-hand side, as you pointed out, everything's going to cancel except our first term and our last term. So we're going to get is this is going to be less than or equal to 1 over 2n 0 minus x star. Oh. That's a little squished, so let me move that over. So does everybody get how we got to this point? Right here. Everybody go with like the telescoping sum and stuff. So we're almost there now. So now we get to work on the left-hand side because this is just an ugly mess. So there is a really neat trick that we can do to simplify this. Does anybody have any ideas? Possibly on how we can simplify that? Probably like the hardest thing to see in this entire proof. So as a hint, it's not really mathematical. It has something to do with what we say about gradient descent always decreasing. He cannot answer that question. He already took the class. Okay, so remember when we said that gradient descent is always decreasing, right? So we're always making, yes.
So each term is upper bounded by first term.
It is upper bounded by the first term. That is true. But
The
no,
lower bounded by last term.
lower bounded by the last term.
So we can replace that by n by k times the cluster.
Yes, because we're dealing with a less than or equal to sign, right? So if we lower bound all of these with this, it's still guaranteed to be less than or equal to this value. Amazing. Oh my God. Let's go. So basically what we're gonna have is we get k plus 1 times f of xk let me not rewrite all of that. Did everybody understand that logic that we just did there? Are we all good? Good? All right. Huh? Thank you, Jordan. Okay. So now basically if we kind of look at this, here's what we're gonna get. I forgot. This is what we have. Now, this is slightly different than the theorem we wrote at the top, and that's because we just chuck some terms out. We quite literally just take them out because they don't matter to us. So recall that this side has to be greater than this side. So if we're subtracting a positive value right here, if we were not subtracting this value, would this inequality still hold? Yes, yes. So basically what we can do is we can say, we don't like you, we hate you, get out of here. Now, we have this k plus 1, and just to make it look nicer, is dividing by k going to yield a larger value than dividing by k plus 1? Yes, so we don't care about the plus 1 either. Bye-bye. And so what we actually have now is almost what we started with. And you asked where the beta comes from at the beginnings. And you recall this entire proof holds on the fact that n is less than or equal to 1 over beta. So we're just going to set n equals 1 over beta. And the proof went over the number of slides I expected it to as well. And hence prove it. And so the thing I wrote before, I just basically, I set this to be epsilon, the difference to be epsilon. And you just multiply this. All right. Oh, no, over here. This is going to be epsilon. And then you can multiply this by k, both sides by k, and then divide by epsilon. And then that gives you the formula for like the number of iterations to get within a certain value. And so, yeah, that is the proof for the convergence of gradient descent within a certain number of iterations. That's the only proof I had planned. So do not ask me for the stochastic gradient one. I cannot do that one. Maybe Neil can. He said no. So we're out of luck then. But yeah. Any questions, comments, concerns? Please don't throw things at me. I'm sorry I put you through all that math. But I give you guys the option to leave. So don't shoot the messenger. All right. Jordan, Sparsh, anything to add?
Not really.
Leo, do you have anything to add? Good.
Yeah. I guess one quick thing, like I forgot to announce before, which is what we're talking about next week. For some reason when we downloaded the slides, this just like did not, this part just like did not appear. This originally here had thank you and then like what we were talking about next week. But basically, I don't know what happened. I love Google Slides. But next week we're planning to talk about something called maximum likelihood estimation, which is like you have your neural network model, right? You have some outputs. How do we actually do something to these outputs, pass it through a loss function, and why are we using those particular loss functions? That's the first thing we're going to talk about.
The second thing we're going to talk about is something called backpropagation, which is how do we actually calculate the gradients, right? We have been using gradients this whole time. How do we actually calculate them? Hint, hint, you're going to be using chain rule. Third part, if we have time, we probably will, we're going to give an introduction to something called a convolutional neural network. And especially for those of you who are in applied track, currently, most of you are probably doing the MNIST tracks. So you're going to be using normal neural networks that we talked about today. But when you move on to the next notebook, the Scipar 10 notebook, you're going to be dealing with convolutional neural networks, and those are kind of the state of the art, sort of, for computer vision today, and you will see why that's the case. So hope to see you next week in the same time, same place. Though when we like with all these concepts, the ones that are necessary to help you like code in applied track, we will also give like short 15 minutes, really condensed versions of it right before you go off and work on the applied track stuff as well. So see you on Wednesday if you're in applied track, and next Monday if you're just doing theory track. Thanks for coming.
Thank you.